All right, on tonight's episode of Python Papi, we're back inside our artificial intelligence course and we're still doing our learning module. Let's have a look at what we went over tonight. Now, last night, if you recall, we went over the process of trying to draw some line to separate this complex model here, where we have our O's surrounding our X's, our O data points surrounding our X data points. And that's what we're going to pick up now. So imagine that our X data points are surrounded by our O data points. If we try to find a line that divides the X data points from the O data points, it's actually going to be difficult, if not impossible. Anywhere we draw a line, there's going to be a lot of errors and mistakes, a lot of what we soon call loss to that line that we draw, a lot of points that will end up getting categorized incorrectly. What we really want is to be able to find a better decision boundary that may not be a straight line through this two-dimensional space. And what support vectors machines can do is they can begin to operate in higher dimensions and be able to find some other decision boundary, like a circle around our X data points, for example, that actually is able to separate one of these sets of data from the other set a lot better. And I drew a circle around our X's the best I could. You can see here we have a circle drawn around our X data points that's separating from our O data points. And you remember that the X's are not rainy days and the O's are rainy days. So yeah, I did the best I could with that. So oftentimes in data sets where the data is not linearly separable, support vectors machines or support vector machines, by working in higher dimensions, can actually figure out a way to solve that kind of problem effectively. And so that then three different approaches to trying these sorts of problems. We've seen support vector machines, we've seen trying to use linear regression and a perceptron learning rule to be able to figure out how to categorize inputs and outputs. We've seen the nearest neighbor approach. No one necessarily better than the other. It's going to depend on the data set, the information we have access to. It's going to depend on what function looks like and what we're ultimately trying to predict. And this is where a lot of research and experimentation can be involved in trying to figure out how it is best to perform that kind of estimation. But classification is only one of the tasks that we might encounter in supervised machine learning, because in classification, what we're trying to predict is some discrete category. We're trying to predict a zero or O data point or X data point, raining or not raining, authentic or counterfeit. But sometimes what we want to predict is a real numbered value. And for that, we have a related problem, not classification, but instead known as regression. Now, regression, supervised learning task of learning a function, mapping an input point to a continuous value. Basically, regression is the supervised learning problem where we try and learn a function mapping inputs to outputs, same as before. But instead of the outputs being discrete categories, things like rain or not rain, in a regression problem, the outputs are generally continuous values, some real number that we would like to predict. This happens all the time as well. We might imagine that a company might take this approach if it's trying to figure out, for instance, what the effect of its advertising is. Like, how do advertising dollars spent translate into sales for the company's product, for example? And so they might like to try to predict some function that takes an input, the amount of money spent on advertising. So we have a start of a function here. We have function advertising. Now here, we are just going to use one input. But again, we could scale things up to many more inputs as well. If we have a lot of different kinds of data we have access to. And the goal is to learn a function that, given this amount of spending on advertising, we're going to get this amount in sales. Let's move down a little bit further. So this is our new function here, function advertising, and this is the function of money spent on advertising, and this should be the money generated by those actual purchases of advertising. So function 1200 equal 58, meaning we generated $5,800 for the company by spending 1200 on advertising. And we might judge based on having access to a whole bunch of data, like every past month. Here is how much we spent on advertising, and here's what the sales were, as I just explained to you. And we would like to predict some hypothesis function. That again, given the amount spent on advertising, we can predict, in this case, some real number, some number estimate of how much sales we spent or how much sales we expect the company to do in this month or quarter or whatever unit of time we are choosing to measure things in. And this is the final function that or not the final function, but the final algorithm that we came up with so far. We have the F advertising, then we have the F advertising money spent, and then we have the money generated by that money spent on advertising. And then we have a hypothesis of what do we plan on doing or what do we expect to do for that month or quarter or whatever unit of time we're using to measure. And that's where we stopped. I didn't want to get too far ahead without fully grasping everything. So yeah, we left it there for the night. But of course, we'll pick it up tomorrow, and I will keep you guys posted every step of the way. For now, this is the Python Papi. You guys stay Gucci.